Okay, we meet again for the next module, okay, which is the introduction to the Verilog code. Okay, so we will cover the basic Verilog and then the construct, okay, which is the number and operators, and also describe the modeling styles that you can use. Like I said previously, that not all the design actually suitable for all the model. Okay, so you have to choose which one that more appropriate. Okay, okay, we look for the introduction for the Verilog itself. So Verilog is a standard languages, okay, for the HDL. Okay, we have two, we HDL and the Verilog. Okay, but Verilog is the latest one. Okay, so originally introduced in 1995. Okay, but now we have enhanced version in 2001. So currently what you will use in these courses actually the version 2001. Okay, so there will be a little bit differ between 2001 and 95 style. Okay, but both can be used. Okay, both can be compiled with the same compiler. Okay, but easier one 2001. Okay, choose. So this Verilog actually originally intended for simulation, but now actually it's used for the hardware synthesis. Hardware synthesis means that you will convert, okay, your design to the hardware. Okay?
Start of operation.
At the start of the operation, yes, as okay, I can accept. Where else? X don't like you don't know the name is don't care, right? Okay, don't care. Okay. When else the X can happen?
It doesn't matter if it's 0 or 1.
Yes. Okay, correct. Means that it doesn't matter. Okay. So if in the decoder, let's say in the decoder, so it doesn't matter either it's 0 or 1. So means that actually you do not need to do connection. Okay. If your value don't care, you do not need to do the connection. Okay. So X can be value 0 or 1, but means that in the Verilog you just can write it as the X. Okay. You do not need to write it as the 0, 1 because 0, 1 means that the solid value. Okay. You can write as the X, so Verilog can understand that. Okay, so the numbers that can have is the binary, octal, hex, and decimal. But common we use 3 only, which is the binary, octal, variable, hex, and decimal only. That we will use. Okay, how to write the code? How to write the value? This value number in Verilog code. Okay, let's say I want to. This is 2217 is too big. I want to write value number my y actually value, let's say number I. Okay, number I actually value 10 in decimal. So you think how I can write the value I in Verilog? Okay, so I equal to
4.
okay. If you look for the format, 4D. Follow this format. Follow this format. How I can write the I in Verilog?
12 bits or 4 bits?
4 bits. Okay. Why 4 bits?
Because 10 is only used for 4 bits.
Okay, because the minimum number to write and value 10 is 4. Okay, so you choose the minimum number of the bit. Okay, you can also write a 5 because still in the range, right? What is the range of binary number?
1 to 7.
No, the standard formula. For unsigned number. This now we work for unsigned number. Let's see. What is the size of the standard value number? Let's say your bit now is n. Your bit now is n. What is the standard formula? Who remembers? Okay, 2 power of n. This because this is actually the unsigned number, should be positive number. So 0 to 2 power of n minus 1. Okay, this is the standard formula. Okay, so means that the range number that can afford number 10, n is equal to 4, the least number. Okay, you can have 5, 6, and 7, but the least number. So now 4. After that, apostrophe here. Apostrophe. After that, D10. Okay, you want to choose now. Okay, because number now can done in 3 ways. Okay, so you have the decimal, you can have the binary, you can have the hex. So you can choose anyway. Okay, you want to use the D, decimal. Okay, decimal, and the significant value, this is number 10. Okay, you can use in this way. Okay, or you also can use in this way. Okay, binary, and the 10 in value value, so which is 10, 10. Okay, or you can use in this way, hex. In hex, sometime in hex, which is in. Okay, so you have many ways. Okay,
Should be capitalized or
can either. Because for the hex, small letter or capital letter is same. Okay, for the hex number. Hex number they recognize both way. Okay, unless the thing that differ. What is it? A and A. Why is differ? A and small letter A and capital A is different. What is it? For hex, no issue.
For moduleN.
moduleN, okay. ModuleN, okay. What else? Let's say regarding about the number system. Number system, which is A, small letter A and capital A is different. Remember, number system that A and capital A is different.
ASCII?
Okay, very good.
Oh.
Very good. ASCII. ASCII code. Okay? ASCII code different. You cannot simply use A or capital A. Okay, but hex okay. Okay, hex number the okay. Okay, so similar. Okay, if I want now to okay. So this is the same thing. So, okay, let's say now you want to write in the negative number. Okay, negative number. Again, must go to the range number. You have to determine. Now it is some sign number now. Okay, so you need to determine the range number. Okay, when we talk about negative number, it will straightly go to 2's complement number. Do not go to any kind number anymore, like sign magnitude, like 1's complement. No, okay, straightly go to the 2's complement number. Okay, what is the range number for 2's complement number? Because you need to know the range, because you want to determine the value of the bit. Number negative 10 should be reside in the which range number, because you want to know n. What is the n? Okay, so the easier way, what I did is I remember for 4 bit. Okay, I remember n equal to 4 bit. If n equal to 4 bit, the range number must be like this: negative 8 to positive 7. I just remember this way. Okay? After that, I can play around. Okay, now, okay, negative 10 cannot be here. So it means that I need to try for n equal to 5. Okay. So n equal to 5, actually there will be the range now. The range number is like this. I can, from here, actually I can come up with the range number. So this means that negative 2 power of n minus 1 to positive 2 power n minus 1 minus 1. Okay? So I can come up with the standard formula. Okay? So this is n equal to 4. So means that negative 2 power 3 negative 8 until positive 2 power of 8 minus 1, I've got positive 7. Okay? So means that I can replace now my n equal to 5. So I can simply replace here. It should be negative 16, right? Eh? There? Negative 16 to positive 15. Positive 15. Okay, it means that negative 10 cannot reside in here, which is n equal to, this is n equal to 4. This is n equal to 5. Okay, so means that negative 10 must be signed in here. So means that my list number, okay, for negative 10 should be 5. Okay, 5 bits. So means that how to write it? You can just simply put the negative only 5 bit. Okay, decimal 10 or negative 5 5 bit 1010. Okay. Okay. This one as well, negative 5 bit A. Okay. Negative 5 hash A. Okay. So we have a few representation of the number system here. So you can see that. Okay, for example, if you have the Z, okay, so Z, it can be written like this way. Okay, so 8 bit. So this is hash Z and 3. So you know, for the hash, each digit represented by 4 bit. Okay, by 4 bit. So means that the number 3, if you interpret, so this is should be 0011. Okay, and the Z also should be 4 times no? Z. Okay. Okay, this is the sum operators in the Verilog. Okay, so you have the big ones, you have the logical, you have the arithmetic. So actually, this is the difference between the schematic and the Verilog. Right? So because if schematic, you only can do the first one only, which is the bitwise. You cannot do all the things in the schematic. But now, if you move on to this Verilog HDL, so you can apply all these operators. Okay, what the difference between bitwise and logical? It seems same. It seems same, like the not, like the negation, like the and, also that seems same. Logical and, that's the or, like logical or. So you think what is the difference there?
Logical you get 1 bit output.
Okay. One bit output. Okay. Which is true and false bit. Okay, very good. Bitwise.
Device, for example, if the input is 2 bit, and then we use this
The output.
so it will become 2 bit.
The output will follow the operand. Okay. Bitwise, so the output, if you output, let's say you A and B. F equal to A and B. A is 4 bit, B 4 bit, must be same bit. So F 4 bit. Okay, F must be 4 bit. But if you use logical AND, let's say A 4 bit and B also 4 bit. Okay, but you must do in this way. this is logical. Okay, this is bitwise. The output F for bit, but this one the output is 1 bit, which is true or false. Okay, true or false. So means that it means, is it A equal to 1? Okay, is it A actually true equal to 1? Is it B equal to 1? So means that logical. Ataupun if in this case 1 bit lah. If I want to make this to 4 bit as well, I need to put all 1 1 1 lah. Okay, ataupun 1 0 0 1. Sama je, okay? Actually same because this is decimal and decimal. So no need to change, okay? Decimal means that even if A is 4 bit, then we will be determine, is it, we test. Is it A equal to 1? N, logical N, B equal to 1. So is it this true? If true, then F becomes 1. If not, 0. We're 1 bit, okay? So that the difference between bitwise and the logical. Okay, very good. So at least you know the where to use it. Okay, okay, arithmetic common lah. Okay, add, sum, multiplier. Okay, in this case, okay, let's say F equal to A plus B. This schematic can do this. Can, right? Schematic can do A plus B, but how it is done?
Oh, thank you. Full edit.
Full adder. What is the full? What inside the full adder?
Oh, right.
The bitwise operator. Okay, the bitwise operator means that the basic gates and or not. Okay, so means that if you use schematic, you don't have the plus. Okay, you don't have the plus. What you have is the bitwise. This one must be translated to the basic logic gate. Okay, basic logic gate. So, but you use the Verilog, then much more easier. You can do the plus, you can do the minus, you can do the multiplier. Imagine how to draw, how to design the multiplier using the bitwise, using the gates. Okay, very hard. Okay, but now just use one line code, multiplier. Okay. Alright, and then you have the relationship. So this one is comparator, right? Comparison, equality, logicality, arithmetic, shifting. The new one is the concatenation. Concatenation means that you just want to combine the bit. Okay, you want to combine the bit, or you want to expand the bit. Okay, let's say now you have the A is 4 bit. A is 4 bit. Let's say 0 0 0 1. Okay, and then you declare output Z as a bit. Okay, as a bit. And then you just want to wire the Z to the A to the Z. Okay, then you just want to wire. So what happened now in the drawing? So this is your Z. This is your A for bit. Z is a bit, but A is for bit. So what happened? You have to concatenate. Okay, another 4 bit. Is that where you want to A ni? Now A is equal to 0 0 0 1. So you want to concatenate to make a bit. So you have to concatenate another 4 bit. Okay, 4 bit, but you don't want to change the value A. So where should be the 4 bit value? In here or in here? MSB, right? In here, if you put in here, then it becomes different. Change the value. Okay, so A will become 0 0 0 0. So This is value 0 lah, I can put in like that. But how to write the code to make A like this? Okay, so you have to use the concatenation. Okay, so means that you have to concatenate A equal to or you want to check Z straightly lah. Okay, Z straightly because Z will equal to A, so this is Z. So you have to concatenate for B 0, 0, 0, 0, comma A. Okay. Okay, conditional operator is like to test. Okay, for example, you have a 1, and then you check. Okay, selector. Okay, is it true? If true, then the Y will assign to value 1. Okay, if not true, then Y assign to value 0. Or I can use the try-state previously. Okay, I want to use the try-state. So this is I, this is Y. So this is En. So if I want to get Y, so I can write in this conditional operator. So I will check. To make Y equal to I, so En must be equal to 0. Logical equal, eh? Okay, is it En equal to 0? Yes. Yes, then Y, I. Otherwise, Y is Z. How to write the Z? No, eh? Wrong, eh? Should be 1 Z. Okay? Remember, because Z is the number system as well. Number, eh? You cannot write the Z like that. If you write the Z, it becomes variable. Okay? So you have to write in the standard of the number. Okay, so we have done this. Okay, we go to the style, model style. Eh? So actually we have 4 styles, okay, for the modeling. Alright, so we go for the modeling. Next modeling, okay, behavioral modeling. So this is the detail for the behavioral modeling. So it is in the order. The statement will be done in the procedural statement. Okay, and then the important thing is the behavioral modeling. In Verilog, we'll use the construct similar to the C. So you can see the writing of the code is like that. We'll use the construct like the if-else, the case statements. So this one we call as the procedural statement. And then you need to write it in the always block. Okay, all these statements. So in the single statement may contain single or may contain more than one statement. So if more than one statement means that you have to write in the begin end. Okay, so must be reside in the always statement. Okay, and then you have the sensitivity list. So if one statement, okay, but if you have multiple statement, you must be begin end. Okay, I think we can go for the activity for this one. Activity 1. Okay, so can use the there is the steps to do it. Okay, the question is you have to write the behavioral model of the 2 input OR gate. Okay, 2 input OR gate. So let's say this is the diagram. So your input is A, B, and the output is 1. So you have to write this in the code using behavioral modeling. Okay, so the statement is if both inputs are 0, then the output is 0. Otherwise, 1. So that is the truth table for the OR gate. Okay. Okay, so you can share the result to the peddler. I give you around 5 minutes, okay, for you to write the code. Okay, can use the input A, B, output Y. The module name you can use the OR. Okay, let's say the module name is OR. OR1. Let's say OR1. Okay. Okay, you can use the sample in the Padlet. Okay, for example, operators or function. That is an example for you to write the code. Okay, the statement if so you can use if else. Okay, I can give the hint if else. Okay. If both input are 0, then logical and then the output is 0. Otherwise, output is 1. Right? So if the input now A, B, you can use the logical equal. If condition logical equal A equal to 0 and logical N B equal to 0, then the Y will equal to 0. Okay, else Y equal to 1. Okay, got it? Okay, if you want to use the case statement also okay, no issue, because as long as you use the behavior model, if else case statement, actually in the inside the behavior modeling. Okay, can write it. It's okay. The bench don't need lah. Okay. Just the design file. Design file enough. If you want to write together with the testament, you can copy the other the background, the available, the Padlet. So you just modify a little bit. Okay, so anyone done? You can share to the Padlet so we can see your answer. Okay, done it.
You need to use an if else.
You can use if else. If you want to use the case, also acceptable. Okay, you can share in here. Okay, got it. It's okay, just share. Just share in the Padlet, then we can do together. Also, no issue. Right, give me done. Okay, share to the Padlet. Benzene already done, eh? Okay. Okay, she already share in here. So very good. Okay, so she used the case statement, also okay. So as long as the input, either one input is 1, then the y should be 1. Okay. However, default actually no needed there. Okay, because you already declare all the bit. Okay, because the bit is already 2 bit, then 4 possible value already there. So default actually no needed. Okay. Right. Okay. Okay, Hakimi, done. Code. You copy the code only.
Yeah, because the EDA using tab cannot allow to share.
Oh, not allowed to share the link. The link. I see. In the.
Just
Oh, I see. Okay. Okay. So give me back in the if else. So okay, very good. So right, oh, I don't see the pencil. Output, okay, very good. So you're aware about the right. Okay, so the output, right, but why not the output together,
Oh
Why not the
yeah.
right together with the Z?
Actually I forgot. Yeah, I can just put red Z
Hmm.
here. So when I write the code, I was like, oh, it's supposed to be registered for this.
No.
So I put red
Uh,
below there.
okay. So so never mind. But it's working lah. Okay, it should be working. Uh, okay, always X Y and then okay, logical operators there. Okay, logical operators and logical equal logical and after that you have the Z equal to 0 else Z equal to 1. Okay, alright, very good. Okay, so the next one is, okay, we go to the further. So we just wrap up, okay, the modeling for the Verilog, okay. So we schematic is the Verilog modeling style. So the schematic only have one model only, but the Verilog can have 3. Okay, so you are allowed to choose which one. Okay, so we already gone for the operators, which is the schematic only for the bitwise. Okay, but for the HDL, all the operators are allowed in here. And a few Verilog keywords that should be remember, okay, in here. So since you have the two kind of the circuit, combinational and sequential. So if the combinational, you can use all the 3 modeling, okay, for combinational actually, okay. But for the sequential, you can only use one modeling only, which is the behavior, okay, behavior modeling only. So you cannot use the you cannot use the structural modeling. You cannot use the data flow modeling. Okay, combinational can all the 3 models. Okay, this is the few Verilog differences between 2001 and 95. Alright, so you can see like this is correct what you said that if the 2001 you can write in a line code everything there. Alright, so you can save a few lines code there. Same like this, alright. So Verilog 2001 must be easier way to write the code. Okay, so we work go for the combinational part, So this one we will cover for the marks, decoder, and the basic construct, okay, for the modeling operators. So since you know that for the combinational, you can use 3 modeling, okay, instead of only like the sequential only one. Okay, so now we want to design, let's say, multiplexer. Okay, so multiplexer by using instead of using the data flow modeling only, then we use the if else. So because if else is much more easier than this. Okay, if I want to change to the case statement, so should be how? Where the part should be changing. Okay, so this one, Okay, very good. So this one. So this one will be case. Okay, case. The rest of it will be sim. Okay. So still output, right? It is still output, right? If you use case, it's still output, right? Is it? If you use case, still, right? Okay, because you still use the always keyword. Yeah, alright. So as long as the variable inside the always keyword must be right. Okay, either you use if else or the case. Alright, so we have a few ways there. And you also can use the conditional operator, okay, for the multiplexer, okay, like this 2 to 1 multiplexer. You can use the sign and then the Z equal to, then test it, okay, S is S equal to 0. If true, then the Z will becomes A, otherwise B. So this is conditional operator. Alright, okay class, we continue for the next design, okay, which is the modeling the arithmetic design. So arithmetic, as you know, is the addition, okay, addition and subtraction. For example, F will equal to A plus B. So this is the arithmetic, right? So all minus, let's say you will use the adder, okay, adder. So to design this means that you will design, you can use in Verilog, you can use either way. If you want to use the operator like this, okay. But if you want to use the structural modeling also, okay. So it means that if you want to use the structural modeling, means you will design the adder. Okay, so you can design the full adder. Okay, the full adder. So it means that this can be multiple bit. Okay, so multiple bit. So full adder will represent 1 bit. Okay, so let's say this is represent for the A and B. So this should be the first bit. Okay, and then you can have another. You can have the output. Okay, so there will be the circle inside here. Then you will have the summation and the carry out. Okay, so this is summation 0, and then you have the carry out. See, normally we put there as C1, and also you will have the C in. Okay, in your full adder. Okay, and then if you want to put, if this is 1 bit, then this should be look like this. But if it's multiple bit, then you will copy paste this block. Okay, a few times. Okay, to represent. So how you can put it in? Actually, you can put how many blocks you will have. Let's say I want 2 bit. Okay, my A and B is 2 bit. So this becomes the B1. This is become A1. So carry in now, C1 go to here, then I will have the S1, then I will have the C to there. Okay, so if I combine together this thing, so I will call this block as the ripple carry adder, RC. Okay, why? Because the carry out is cascaded. Okay, cascaded from the beside block, from the neighbor block to the next block. So that's why we call it as the ripple, ripple. Okay, how to model this arithmetic or this adder or this RCA in the Verilog code. Okay, so let's see through the activity 3. Okay, so the first one, you have to sketch the functional block. Okay, let's say for 4-bit RCA, but what I do now is for 2-bit. Okay, so means that you need to expand another 2 blocks. Okay, to get the 4-bit RCA. Okay, and then you need to write the code. Okay, for this structural modeling. Let's say I want you to use the structural modeling. Okay, so means that you have to call 4 times. Okay, so this is the block name FA. Okay, so you have to use the structural modeling. Okay, you need to instantiate this module FA 4 times. Okay, can you do that? And then share in the Padlet. Okay, number C is to modify the code in the B using data flow model. Alright. After that, try to conclude. Okay, what the differ between the code number B and number C? Right? Okay, you done, you can share in the further, okay? Okay, since this is the combination one, you can use 3 modeling, but now I want you to use the structural modeling. Okay, very good. Okay, Nazmi has come up with the answer. Okay, we can look for the answer. Okay, so you call in the module FA, so you made it in the module FA. After that, you call it in the module RCA for B, and you call it using the structural modeling 4 times in here. Okay, very good. Right, the rest. Okay, another one is what you need to do is to write the code in data flow modeling. But never mind, we can hold that. So we wait for the others because I want to show the difference between the model. Okay, mention already done. So, okay, you send in here. Okay, this is what Vincent used. The same. So she used the array. Okay, array method. Actually same like Nazmi did. But Nazmi one code line by line, sure. Okay, what Nazmi shows, what Nazmi did. So he write the code line by line. You can see line by line. FA1, FA2, FA3, okay, FA0 and so on here. Okay, but Vincent use the array, which is the array is represented in this way. So it still means that FA0, FA1, FA2, FA3. Okay, so you just write in one line code only. Okay, one line code only, but it is represented in the array. Okay, array. Okay. Hakimi, can you do in the data flow? Data flow modeling. Because the question now asks, this is the structural modeling. So Nazmi and Vincent, then the next is to use the data flow modeling. Okay, data flow modeling should be much more easier there. Dah.
Share lama.
Oh, you share kat mana?
Ya, banding.
This one?
Yes.
This one, eh? Okay. Okay, still same lah. Still use the structural modeling. Okay, never mind. Alright? Okay, alright. So now the question is asked to change or modify it using data flow modeling. Okay. So now you know this is the F is equal to A plus B. Okay, and you know A and B is for bit that you use now. So the data flow modeling actually is Boolean. Is it correct? Represent the Boolean equation, right? Data flow modeling. What is the keyword for data flow modeling? Use it? Assign. Okay, very good. So now I want to, this is structural modeling. And this is data flow. Okay, so now I will use assign keyword, and it is similar for the Boolean expression. This is your Boolean expression. So now it should be F equal to A operator. Use the adder operator. Add. Just add B, and then you have the C in as well, right? Okay, so plus the C in. Done. Okay, only one line code only. Okay, instead of you use the structural modeling. Okay, so is this correct, or you want to do some modification? A and B is 4 bit. Do you agree this the answer, or you want to do some modification?
Maybe the output.
The output.
F. And separate it into sum and carry.
Okay, very good. Okay, so you can do it this way as well. Sign, then you have to concatenate, right? Concatenate C, comma S, because it is represent the C and S. Okay, C, comma S equal to this A plus B plus C in. Okay, another, if you want to modify, what else? You think? Najmi, you think, what else? This one is not in the same bit. This is 4 bit, 1 bit. what you can do. This is 4 bit. 4 bit plus Cin is 1 bit. What? Concatenate as well. Make for the Cin as 4 bit as well. Okay, so let's say I can change directly from here. So this is becomes this is already a 3 bit, okay? 3 bit 001. Sorry, 3 bit comma Cin. 000 comma Cin. Okay, very good. Okay. So you can see the difference between the data flow modeling and structural modeling. Yeah? So this is the time that you can think, okay, which the model that appropriate, that suitable, or the faster one. Okay, so I bet that you may choose the data flow modeling. Okay, it is only one line code. Okay, in other way, this means that structural is much better. Okay, so that's why you have to define. Okay. In your design, which the model that will be appropriate for the things. Yeah. Okay, so we go to the parameterization and scalable modules. Okay, and let's measure that. Alright, the concept of the parameterization. So now, when you design this or this, you already assign the value as the scalar value. Means that you already declared A and B as the 4 bit directly. A, B, something like that. Okay? And then, if you want to use the different bit, then it's quite difficult because you have to search all the bit way. Where is the area you need to change the bit? Okay? Why not you just make it flexible? Okay, so that's the meaning that where we can use the parameterization. Okay, so we make this do not use as the scalar value, but use as the variable. Okay, so let's say I use the n variable, so I can put n minus 1 there. Okay, so I need to declare the parameter n. Okay, so if you use this way, so I have to declare parameter n. N now equal to, let's say, what are the value? Okay, let's say I put 4. Okay, so means that if I want to change the value, I just change in here. Okay, the rest of it will follow. Okay, so that's the concept for the parameterization. So parameterization actually to make the design is more flexible and customizable. So and it facilitates the design use and increase the design productivity. So you have to use the keyword parameter, and also comes with the variable that we call it as the named parameter passing. Okay, this is the example. Let's say, okay, you can change the size of the AND gate now. Okay, any value bit, just change at the end in here. Yeah. So the rest will follow it. Okay. Also, if you use the adder, okay, let's say the parameterized adder. Okay. Now I want, before I put A plus B is 4 bit. Now I want to do for 16 bit. Okay, so you can use in this way. Okay, you have created the 4 bit, and it is waste if you just throw away that design. Okay, why not you just reuse that? Okay, the adder design with 4 bit, but you use the features parameterization in the Verilog to change the value to 16 bit. Okay, so you allowed to do that. So let's say you have done that. Okay, let's say in this case 8-bit. But now you just call this design back, okay, and change the bit value. So how you change call, you can use the structural modeling as usual. This is where the structural modeling benefit. Okay, so especially when you want to do the parameterization. So you just call back. Okay, just call back this module, but change the value now. This is we call as the passed parameter, name parameter passing. You just change in here only. So now your original is .n. .n is 8, but now you change it to the 16. So means that now, and then you do not need to declare. Okay, again the operator of the adder, it will use the same declaration in the module, in the module N now. So here you just call it this module and change the bit only. So what you did, if you run this code, is that you will do the addition for 16-bit. Okay, so that's the features in here that make the design more flexible. Okay, activity 4. Okay, in this activity, modify the question previously in activity 3, B and C using parameterization. N equal to 8-bit, N equal to 16-bit, N equal to 32-bit. Okay, previously what you did is you can use the structural modeling. Okay, previously you used structural modeling and you also use the data flow modeling. Okay, then in here you just call this module back, change to this new bit only. Okay, so I think the easy way is use the data flow modeling. Okay, just use this line code data flow modeling. Okay, let's say you use the 4-bit now. Previously you use 4-bit, right? After that, you just call this module, change to the n equal to 8, n equal to 16, n equal to 32. Okay, try to do this and share here. Okay, you can use previous module that you have previously. Okay, just call back this your module name. Okay, if you use structural modeling, it's okay, no issue. Okay, just call back your module name and then change. How to change? Just follow this this one. This one. So this is your original module. Then you just call it back. Just call it back your name of the module and then just change to n equal to 8, n equal to 16, n equal to 32. Okay, remember that the parameter, the original value can be bigger than you want to design or can be smaller. Okay, for example, this one can be 32. Okay, can be 32, but you want to design 16, no issue. Or this one maybe can be only 4-bit only, and you want to design 16, no issue. Okay, so that is the flexibility, okay, of the parameterization. because the reusable of the module actually one kind of the design that we want to achieve. Okay, the objective of the design we want to achieve. Okay, which is the reusable module. Okay.